Nuclear physics. We're going to go through some questions today, all to do with nuclear physics for A-level physicists. Lots of multiple choice, but we're going to pull out different parts of the spec as we go through. So I hope you enjoy. So this first question here, we've got to use E equals mc squared. Even though it's not obvious, we're trying to work out the maximum power output. Now, power is just energy per second. So we're going to use E equals mc squared. But first of all, we need to find out, to be able to use energy per second, because that's what power is, that's joules per second, we're going to have to work out how much mass is released per second. We've currently got it per hour. So the mass per second, or kilograms per second that's released, is going to be 9 times 10 to the minus 6. And then we're just going to divide it by 60 squared to get it in to be per second. So once we then do that, and that gives us 2.5 times 10 to the minus 9 kilograms per second, we can then just go ahead and use it with this equation. We're trying to find the power, but it's per second. This is in per second. So we can basically say power equals the mass per second, so 2.5 times 10 to the minus 9. And we got to times it by speed of light squared. So that's obviously 3 times 10 to the power 8 all squared. And we should find, if we plug those numbers into our calculator, gives us 2.25 times 10 to the power of 8, which is option A, is what it rounds to in this question. This question is about closest approach of a particle. In particular, it's a particle, an alpha particle, getting close to a nucleus, and we should know that there's a distance, a minimum distance it can get to before all of its kinetic energy gets transferred to electric potential energy, and then it sort of gets feels a repulsive force from the nucleus itself. So we're asked to work out which of these statements is correct from here. So acceleration being 0 at p, it's definitely not going to be 0 because it's slowing down and changing direction. So it's definitely not going to be 0. Is kinetic energy being greatest at p? It can't be. Its velocity is going to be very, very low at that point, so it's going to definitely be faster here than there, so its kinetic energy will be faster here, so it can't be option B. Its potential energy is actually going to be its greatest at p. What happens is all its kinetic energy early on gets converted to potential energy closer to the nucleus, so that leads us with speed is least at p, which we've already mentioned. That's option D. This question looks like it might take you a while, but trust me, it's not too bad. Cobalt-60 has a half-life of 5.27 years. The total activity is 1 gram, and we're talking about cobalt-60. So we're trying to find the total activity. There's a couple of equations we could use. You might think to use the exponential decay equation. You might think to use, we've got activity equals lambda, the decay constant, times by number of molecules. Now, this one here, we don't know the time taken, and also we don't know the initial value, so we can't use that at all really. We are going to end up using one of these. Whenever you see the idea of half-life and you think, I'm going to have to use one of these equations, the first thing that should step into your mind is the idea of finding the decay constant. So the decay constant given to you on your equation sheet is going to be equal to natural log 2 divided by the half-life. This has to be in seconds, so that's a little bit of work to do straight up. So ln 2 to find this out, divided by, so 5.27 times by days in a year, times by hours in a day, times by minutes and seconds, and if you do all that, we'll get a value of 4.17 times 10 to the power minus 9. That's only half the job though. We've got this part, we've got to find out a number of molecules. They've been a bit sneaky here. They've given us 1 gram, and we've got to figure out how many particles there are. Now we should know, if it tells you the mass number, in, for example, cobalt-60 would have 60 grams, would be 1 mole. Now 1 mole is going to be Avogadro's number, 6.023 times 10 to the power 23 particles or molecules, which is what we want to try and find out. The only significance behind 60 is because it's cobalt-60. If it was carbon-14, it would be 14 grams. If it was helium, it would be 4 grams. Okay, so we have to work out, we've got 1 gram of it, so we have to do, therefore, in 1 gram, that's going to be equal to a 60th of the Avogadro's number, because we've got 60th of a mole. So therefore times that all together, and if I'm trying to find my activity, I've got to multiply my decay constant, so this is seconds to the minus 1, 4.17 times 10 to the power minus 9, times by all this value over here, so 1 over 60 times Avogadro's number. Probably should have just written the symbol, to be honest. If we do all that, we get an answer of 4.19 times 10 to the 13, which gives us option A for this question. Closest approach can be one of those questions that can be a little bit long to work out, but the actual theory behind it isn't too bad. You've got an alpha particle moving close to a gold nucleus. There is going to be a distance at where all its kinetic energy gets transferred into potential energy, electric potential energy, and it sort of stops in its tracks, comes and goes back this way. We're trying to find the distance. The idea of closest approach is the distance at which that happens. So it tells us the kinetic energy is 9 times 10 to the power minus 13 when it's a certain distance from the nucleus, and it's got 79 protons in the nucleus. That's kind of all we need. So let's look at our equation for electric potential energy. Now, because we said it all comes from kinetic energy, we're going to write out our equation, but electric potential energy we do already know, because we know that all the kinetic energy gets transferred into it in our equation, which is always quite nice. So from here on in, it's just a matter of finding R. So 9 times 10 to the minus 13 equals, and I'm just going to leave this in constant form, but you can find this in your equation sheet. And there are two charges, as you've got to be careful with this, because we've got 4, because it's an alpha particle, not 4, sorry, 2. So 2 lots of, I'm just going to say E for the charge on an electron, times by, and then in a gold nucleus, we've got 49 E. Okay, so be careful with those two, and then divided by R. If we arrange all this for R, we're going to then have, just to put all our values on this side versus the other side, so we're going to have 1 over 4 pi epsilon 0, and this time we've now got, so I'm just going to leave it in simple form, so 2 times 49 is 98 E squared, so that's 1.6 times 10 to the minus 19. If in over here, and then if we are able to sort of finish off this sum, we should find the closest approach is going to be closest to this value here, 10 to the minus 14. Ones we can exclude straight away are going to be D. That's way too big for an atom. This is a bit too small for an atom. It's usually going to be 10 to the minus 14, sometimes minus 15, but one of these two you could eliminate the other ones straight away, really. This question might take you a little bit of time if it was a multiple choice question, but it could come up as a 2, 3, 4 marker type deal. We've got information about some radioactive nuclei used in exit sites, pretty worrying. But when they're manufactured, the activity is 37 becquerels, so that's our A0. After 10 years, the tritium has gone down to 21. And what's the activity 15 years after it was manufactured? Now, you might be able to find an easier way. Let me know if you do, but I think the easiest way to work it out is to work out the decay constant first of all. So we've got to use the exponential equation twice, really, which is a bit of a pain, but it's got to be done. So what we've got first of all is that it went down to 21 megabecquerel in 10 years. So therefore we've got 21, and I'm going to leave it in megabecquerels because I've got on both sides of the equation. Don't need to waste time doing that. And then I've got the decay constant, which I don't know, and that's 10 years. I'm going to find the decay constant in years because the next value is in years as well, so we don't need to worry about that too much. But if you take logs of both sides, so ln 21 over 37 equals minus the decay constant times by 10, you should then find the decay constant, so divide that value by 10 is equal to 0.056639, etc. years to the minus 1. Once we know that, we're trying to find 15 years after it was manufactured, what's the activity now? So we can put this all back into our equation and say, well, A0 is going to be the same, but now we know the decay constant, so we can sort of put that in to find A. So we've got 37 is our initial activity, E times to the power minus our decay constant we now know. Don't round it too early here because these are all kind of similar to each other, and the time taken is 15 years. So if we do all that, we put that onto your calculator, you should get an answer about 15.8. That's megabecquerels, which leads us to answer C, which that rounds to in this question. This question here, we don't only got ratios to use, we don't have any numbers specifically in this question. We've got a half-life of a material X, which has 6,000 years as its half-life, and then we have another nuclide or sample Y, which has 3 times the number of nuclei, but 6 times the activity. So I'm hoping it's obvious the main equation we're going to use is this one here. So activity equals decay constant times by number of nuclei. The half-life of nuclei Y is not in this equation though, so decay constant is equal to ln 2 divided by the half-life. We're going to make use of this equation as well. So what we're going to do is just a ratios question, is sort of plug in to this value here, and now just because it's ratios, I'm just going to say it's 1 over, because ln 2 is a constant, we're not changing that, the half-life, and then let's try and put our numbers in for number of nuclei and activity and see what we get. So number of nuclei has gone up by a factor of 3, so therefore we've got times 3 to this side, activity has gone up by a factor of 6. So if I rearrange this for the half-life, I've got 6a over n to 3 is equal to 1 over the half-life. And then flip both sides of it, we've then got, I don't know why I put 3 there, there we go. We've then got half-life is sort of equal to, or proportional to, I should say, sorry, is proportional to 3n over 6a. So 3 over 6 is equal to a half, and therefore it's going to have half of the original material's half-life, which gives us 3,000 years, because it was 6,000 years to begin with. We've got a question about nuclear fission here, and before we go into it, we're going to have a look at binding energy and binding energy per nucleon, because that's going to help us answer this question. So we've got a bunch of statements here about this fission reaction, and a lot of them talk about binding energy or masses. So we're going to deal with each statement at a time and figure out which one might not be true and which ones might be true. So let's do first one, which is this material here has an atomic number of 57, has a greater binding energy per nucleon than the other 3 nuclides. So if we have a binding energy per nucleon graph, I'm just going to draw out very, very roughly here, we should know it peaks at iron. So iron has an atomic number of 29. Everything else after that has a steadily decreasing binding energy per nucleon. Now, nuclear fission occurs because elements like uranium, particularly uranium 235 here, want to split into 2 different fragments that have an increased binding energy per nucleon. They want to gain more binding energy to become more stable. So both of these elements here have a lower atomic number, and they therefore have a higher binding energy as you go along. So we've therefore got this material here, so we'll have, let's just call it La here, and we've got Br over here. I know it's not to scale, but hopefully we can see that actually, if we know this graph carefully, we know this one's got a lower atomic number, so 35 versus this one, 57. So therefore, actually, this one's going to have a greater binding energy than this one. So that disproves statement A. So already, actually, we know statement A is not true. Let's go through some of the other ones, though, because it's good revision anyway. The mass is greater of this one than the sum of the particles. Yet we should know that is that the greater the mass of the initial particle is going to be greater than the mass of products that come from it. That's why there's sort of energy released in the form of E equals mc squared. Mass of, can I say reactants? Yeah, let's say reactants, you know what I mean, but it's on the left-hand side of the equation. Reactants, can't even spell it. The binding energy of neutrons is 0. That's not true. Sorry, that is true, beg pardon. Neutrons aren't like bound to anything. So statement C, this one is true, and neutrons by themselves aren't bound to anything. To have binding energy, you need to be more than 1 nucleon. Next one, the binding energy of this one is greater than binding energy of this one. That's not true, because we just said uranium is further down this slope. So our uranium 235 is going to have less binding energy. So all these are statements that are true, apart from this one up here, which is not true. Option D doesn't say binding energy per nucleon, it says binding energy. So if you were to sort of times together the binding energy per nucleon of uranium times by 92, you definitely have a higher binding energy per overall than our material here. So this one is also a true statement. These are all true, so therefore A has to be the correct answer here, because it's not true. Okay, let's talk some NZ graphs or NZ plots here. So we've got, this is an NZ plot. We need to know this is the line of stability. So it's called non-radioactive. So these are the list elements that are stable. Everything either side of them and towards the top can undergo either alpha, beta, decay, or a bit of fission as well. So we're after a nuclide which is got an atomic number or proton number of 45, and it's got a total mass number or total nucleon number of 115. So let's try and find it on the graph first. That will help us out. So 45, I'm going to do it without a ruler, but you should definitely do it with a ruler. We need to know this is number of neutrons. This is not the total number of nucleons. So the number of neutrons in this material would therefore be what we got. That's going to be 70 neutrons. So 70 neutrons means we go up here, up here, up here, and we sort of reach this part here. So there's our element there. So 45 protons, 70 neutrons. We should know about all the different regions on this graph, which one is more likely to undergo each type of emission. The correct answer here, because it's got an excess of neutrons, the idea is neutrons are going to decay quickly into a proton. We should know it also decays into a beta particle, an electron, and an antineutrino. So this is known as beta minus. minus decay. If you have an excess of neutrons or a neutron-rich material, that's what happens quite commonly. The reverse is true. If the material be down here, then you'd have positron emission, because you know that positron emission, we got a proton going to a neutron plus a positron and a regular neutrino. So this would happen if you had too many protons, but in this case, this is the element we're talking about, so it's just beta minus emission.